Welcome to this lecture series in linear algebra. We will continue our discussion with bilinear forms, and in this lecture we'll look at the notion of the matrix of a bilinear form. So let us recall what we have done. We defined the notion of a bilinear form. So if V is a vector space over the base field capital F, then a bilinear form on V is a map from V cross V to the base field, such that if you freeze the first coordinate, then you get a map from the vector space to the base field, and this is linear for all vectors in the vector space. And similarly, if you freeze the second coordinate, you again get a linear map. So that's what a bilinear form is. And the set of all the bilinear forms on a vector space V is in itself a vector space. The addition is pointwise and the scaling is pointwise. We saw that this vector space is actually in a natural way same as this vector space. So what was the identification? One direction of the map was, so the map from this to that, which we wrote as capital theta, was F going to LF. And now what was LF? So LF is a map from V to V star, of course. What does it do? It takes V to, or maybe U to SU blank. So that's what LF is. Okay. Let's continue. This is one problem. It's just basically an example as to how to construct a bilinear form from a given bilinear form. All right, it's an interesting exercise. And now let us get started. So fix a bilinear form on a vector space V and let B be a basis, V1 up to Vn, on the vector space V. Then the matrix of F with respect to the basis is defined as the n cross n matrix, or rather an n cross n matrix, the n cross n matrix is the better English, the n cross n matrix, whose ijth entry is this guy. So the ijth entry is, just evaluate F on this pair. It's a natural definition. And what the next lemma says is that the identification between this and that is something that extends to this definition. I'll explain what that means. So you have a bilinear form on the vector space V. Its avatar in this picture is that guy. And either you take the matrix of the bilinear form with respect to the given basis, or you take the matrix of the avatar with respect to the given basis and its dual. And those are the same things. So the dictionary between the two different representations of this guy is extending to the notion of matrices as it should. This should be expected, this kind of result. Anyway, this is not some deep result, but before we prove it, let us recall what this means. So B star is, by notation, a basis whose elements are V1 up to Vn star. So how is Vi star defined? It is, of course, a linear map from V to the base field, which is defined by this equation. So this is the definition of the dual basis. And now let us prove this quickly. So we want to show that the ijth entry of this guy is same as this thing. Okay, so to find the ijth entry, what do we need to do? We need to first express this as a linear combination of the dual basis vectors and pick out the coefficient of Vj star. That's the definition of this guy. So let's say this is equal to alpha 1 V1 star plus dot 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 alpha n Vn star. Okay. So what do we get? This can also be written as, by definition, this is equal to f vi blank right? So to f vi blank, we will feed vj. So if we feed vj to it, okay, I'll not skip a step. This is equal to, okay, I'll be using the summation notation. Right, and what is this? By definition, this is the left side is what I wrote, and the right side is that which is equal to alpha j, because only the jth term here survives. So indeed alpha j is that, and this is what we wanted to show, because alpha j is the ijth entry of this guy, right? That's by definition of this matrix. So alpha j is equal to that, and hence this equation holds. So that was that. And now let us see a very, very simple example. So recall we looked at this bilinear form. If V is this coordinate space Rn, then we have this bilinear form where of course x is x1 up to xn, and similarly for y. So with respect to the standard basis, what is the bilinear form of f? So the matrix of f with respect to the standard basis is the identity matrix. And this is an exercise. Right? So the diagonal entries are all 1 and everything except the diagonal entries is 0. Prove it, it's very easy. And lastly, let's state at least what is the change of basis theorem here, if you like to call it that. So it's very simple. Suppose we have a bilinear form that is fixed, and we have two different bases. One is this guy, one is that guy. And we can make the matrix of f with respect to the first basis or the matrix of f with respect to the second basis. And one would naturally like to know what is the relationship between these two matrices. And the relationship is very simple. So let's say Wi is summation j equals 1 to n Pij Vj. So each vector here, of course, can be expressed as a linear combination of these vectors. So let's say the coefficients that we get or the scalars that we get are denoted by Pij for all I 1 to n. So then we have this matrix, which we will call capital P. Maybe let me use small p here. So the capital P matrix is defined as the n cross n matrix whose ijth entry is Pij. So then the matrix of f with respect to the second basis is P transpose the matrix of f with respect to the first basis, P. So recall the transpose of any given matrix is just replace the ijth entry with the jith entry. So that's the transpose of a matrix. And this equation is just a simple exercise. Okay, so this is it for this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.